Okay, so after talking about the different kind of nutrients available for the microbes and how they are being absorbed by the microbes and how they are being used for growth and later how they are being manipulated or utilized by the microorganism. Now the next step would be to how those nutrients they are taken up by the microorganism and metabolized. So in this particular lecture, I will be talking about how the metabolism takes place in the microbes. So before we talk about the different molecules, so I would like to talk about a couple of general topics first. So that is energetics and enzymes. So microorganisms, they must be able to conserve some of the energy released in its energy yielding reactions. So as all of you might be aware that in microorganisms, there are a lot of reactions which are going on. So there are either breakdown of molecules or there are production of new molecules. In both the steps, the energy involvement is there. Either energy is utilized for making new molecules or it is being released while the already large macromolecules are being degraded. So energy, it can be defined as the ability to do work. So whenever there's any kind of reaction taking place, either building something, some macromolecules or degrading already existing macromolecules, energy is required. This energy is usually measured in kilojoules, which is in short written as kJ. This is the unit of heat energy. So all chemical reactions in a cell result in changes in energy. So either the energy is required for the change or it is released during the reaction. Now there's a term which is called free energy. So this is abbreviated as G. So this is the energy available to do work. So this energy facilitates the kind of reaction that will be taken place, either the makeover or the degradation or breakdown of the already existing molecules. The change in free energy during a reaction is expressed as delta G0 prime. So this delta in general stands for change. This 0 and prime, they are kind of superscripts of the free energy. If they are there, it means they are standard conditions. So what are those standard conditions? They are pH 7, 25 degree centigrade as the temperature, and 1 atmosphere of pressure. And all the reactants as well as the products, they are measured in molar concentrations. So let's imagine there's a reaction which is taking place. A plus B, it leads to the formation of C plus T. Now, if this delta Z0 prime for this particular reaction is negative, the reaction will proceed with the release of free energy, the energy that cells may conserve as ATP. Now, in these kind of reactions where energy is released, they are called exergonic. So if, let's say, delta Z0 is positive, it means that there will be energy which is required by the reactants A plus B to form C plus T. And those kind of reactions are called as endergonic. So now here I would like to introduce a new term which is free energy of formation, GF0. So this energy is released or required during the formation of a given molecule from the elements. So usually elements, they exist in nature in their elemental form, which are electrically neutral forms like carbon, hydrogen and nitrogen. So their free energy is 0. So now if they are utilized for the formation of bigger molecules, then definitely there will be energy requirement. So if the formation of a compound from its element proceeds exergonically, it means that if the energy is released while formation of large molecules from these simple elements, then we call it is exergonically. So in that particular case, this ZF0 will be negative. So wherever you see negative, it means the energy is released. And if the energy is required, that the reaction is going endogonically. So in this particular case, ZF0, that is the free energy of formation, will be positive. So right away, looking at the notations, that is ZF0, positive or negative, we can right away say that the reaction is exergonic or endergonic. So for most compounds, GF0 is negative. So it means that if simple elements are taken and if they are resulting in the formation of bigger molecules or larger macromolecules, the energy will be negative. It means the reactions will be exergonic and they will be favored. So this ZF0 is calculated by subtracting the sum of the free energy of the formation of the reactant that from the products. So it means that if we consider this above reaction again, so if we go by this ZF0 calculation, so it means that C plus T energy should be more as compared to A plus B. So if we subtract the A plus B from C plus D, we should be getting what is called ZF0. So look at this particular table here. So here there are the compounds which are of biological interest: water, carbon dioxide, hydrogen, oxygen, ammonium, nitrous oxide, acetate, glucose, methane, and methanol. And these are the free energy of formation of these compounds. So if we look from this particular table, let's say we talk about the hydrogen or oxygen. So they have zero energies of formation. It means that there will be no energy liberated in their formation. So they are already elemental stable forms. So if we are any kind of reaction is going on, so let's say for example glucose, the energy is quite high. In fact, this is the highest in this particular table, minus 917.3. So it means that if this particular glucose molecule is formed from the elements or the basic reactants, the high amount of energy will be released. And similarly, following to this, carbon dioxide and water, they also release large amount of energies. So the delta G, the free energy chain that occurs under the actual conditions given by this particular reaction, delta G is equal to delta G 0 prime plus RT log natural K. So this is the delta GS ideal conditions. This is the RT, which are physical constant, log natural, and K is the equivalent constant for this particular reactions. So now I would like to introduce another term which is called the activation energy. Now let's say there is any kind of reaction going on. So A plus B will lead to the formation of C plus T. So in order for the A plus B to form C plus T, it need to overcome a barrier. And that barrier is nothing but a activation energy. So I don't know if you have experienced that initially, let's say you want to start cycling. So in order for you to start the cycle roll, you need to apply a kind of force or a kind of pressure onto one of the pedals. So that pressure or that force is kind of activation energy, which is required in different kind of reactions. It's kind of analogy, you can say, is that initial pedal is more force, and later, when the wheels start rolling, you don't feel that you are applying that much force. So similar to that, so when a reaction needs to be done, a large amount of energy is required. So this particular activation energy, the energy required to bring all the molecules in a chemical reaction into the reactive state. So reactant A or reactant B, they will be kind of not coming close together enough. So in a reaction that proceeds with net release of free energy, it is an exergonic reaction. So now let's have a look at this particular graph. So this is on the x-axis, we have progression of the reaction. Y-axis, we have free energy. So this is the condition, the red one, where we have no activation energy. So if there is some activation energy is given, then obviously it goes down. The free energy goes down. So substrate A plus B, their activation energy goes down. So that leads to the formation of product C plus D. So this activation energy is virtually insurmountable in the absence of a catalyst. So usually the reactants A plus B, they will never react until unless they are given a platform to react. So just imagine that two strangers are sitting in a room. So until unless they have something in common to talk about, they'll not talk. They'll stay quiet in that particular room. So similarly, these molecules, until unless they are coming together or they are brought together with the help of some, let's say, a catalyst or let's say some kind of energy, they will not react. So catalysts such as enzymes, they lower the required activation energy. So initially there's a large amount of energy which is required, as you can see in this particular graph. So if we have any kind of catalyst, then that particular energy is lowered. And this lowering of energy will lead to the favoring of the reaction or the progression of the reaction. So a catalyst is a substance that lowers the activation energy of a reaction, thereby increasing the reaction rate. So catalysts, they facilitate reaction but are not consumed or transformed by them. So you might have noticed in organic chemistry also, sometimes we write A plus B equals to C or A plus B equals to D. And on that arrow, you see some palladium or platinum. So those metals, they are acting as catalysts. So those metals, they are not utilized. However, in biological systems, we are using a different kind of catalyst. So these biological catalysts are enzymes. So enzymes, they are the proteins, and sometimes RNAs, they also act as catalysts. So that are highly specific for reactions they catalyze. So let's say we have enzyme plus we can have a substrate, that enzyme plus substrate complex, and that will ultimately lead to the product formation. So until unless we have something which will facilitate this step, we will not be having this particular reaction. So here this enzyme is kind of favoring the reaction. It is binding to the substrate. So that substrate could be multiples. So that binding of different substrate will lead to the formation of this enzyme substrate complex and ultimately the product. So the enzyme is much larger than the substrate. And the portion of the enzyme in which substrate bind is called the active sites. So usually enzyme, they are large macromolecules. So those macromolecules, they are specific sites where these substrates, they can bind. It's not that they can go and attach anywhere. They usually bind to specific pockets which are designated to specific substrates. So these enzymes are highly substrate specifics. So enzymes, they may, although they are proteins, they may contain small non-protein molecules also. So that participate in the catalysis but are not themselves substrates. So substrates are usually used up in that particular reaction to give the products. So we can have prosthetic groups. They bind very tightly to the enzymes. They are usually covalently and they are permanent. So we can have heme groups in cytoplasm, which is kind of with centrally connecting iron molecules. Then we can have coenzymes. So these are loosely bound to enzymes. It may associate with a number of different enzymes. So most coenzymes, they are derivatives of vitamins and NAD plus or NADH. Okay, so enzymes, they increase the rate of chemical reaction anywhere from 10⁸ to 10⁻20 times. So now you can see this is a huge increase in the rate of chemical reaction. So that is kind of the requirement that the enzymes have. So there are two steps to catalyze a specific reaction. So number one is binding its substrate. So in order for an enzyme to catalyze a reaction, it takes two steps. The first one is the binding of the substrate. Substrate needs to be attached to the enzyme in order for it to react or in order for it to give the products. Position the substrate relative to the catalytically active amino acid at the enzyme's active site. So it is not that it binds, the substrate binds anywhere. It needs to be positioned in such a way that the active site of the enzyme is available for the binding of the amino acids which are onto the enzyme substrate. So these enzymes, they can also catalyze reactions that require energy converting energy poor substrate into energy rich products. So most of the microbes, as we already know, they are growing in poor nutrient conditions. So in those poor nutrient conditions, there are elements or there are molecules which are poor energy substrates. So now those poor energy substrates, they can be converted to rich energy products. So all enzymes are reversible in their activity. So enzymes that catalyze highly exergonic or highly endergonic reactions also. So these enzymes usually which are kind of pursuing reactions which are not that endergonic or exergonic. So those enzymes, they can be used again and again. However, in those cases where high energy is liberated or high amount of energy is required, so in those cases, the reaction is unidirectional. That is, it only goes once and the enzyme needs to be recycled. Okay, so let's move to another topic, which is oxidation, reduction, and the energy-rich compounds. So before we talk about the energy-rich compounds, so let me introduce two terms here. Number one is the oxidation, another one is the reduction. So oxidation in simple terms is the removal of electron or electrons from a substance. So let's say we have a molecule or let's say an element which is available and it can give up electrons. We can say that it has the oxidation capability. And if we have on the other hand, reduction is the addition of electrons or the electrons to a substance. So let's say this particular reaction here. So this hydrogen H2 has an electron donating capability. So it donates 2 electrons and it gets 2H positive charge. And now this half O2 has an electron accepting reaction. So this accepts the 2 electrons and it becomes O2 negative. Now this O2 negative, it kind of joins those 2 protons and ultimately leads to the formation of water. So overall, what we can say is that this hydrogen acts as an electron donor. And this water, this oxygen is an electron acceptor, which leads to the formation of water. So here we can say that the oxidation is taking place of hydrogen and reduction is taking place of the oxygen, which ultimately leads to the formation of water. So substances, they usually differ in their tendency to be electron donor or electron acceptor. So this is quite obvious. So depending on the chemical composition, the substances or different molecules, they could be either electron donors or electron acceptors. Now this tendency of giving or accepting electrons is known as the reduction potential, which is represented as E0 prime. And this is usually measured in volts. So in redox reactions, the reduced substance of a redox couple whose E0 prime is more negative donates electron to the oxidized substance of a redox couple where E0 prime is more positive. So what I mean to say is that if we have a reaction where we have 2 molecules and they both are having some reduction potential. So usually the electrons will be donated by the molecule which is having negative reduction potential to the molecule which is having positive reduction potential. Okay, so redox. So from this we comes to something called the redox tower. So now, depending on the capability of the molecules, or you can say depending upon the reduction potential, we can construct or we can have a tower kind of structure. So if you look from top to bottom, the value of the reduction potential is reducing. From highly negative, it is going to positive. So in a way, you can say that these molecules, they are capable of donating electrons. They are good or strong electron donors. And these molecules which are having positive, they are electron acceptors. So if we say redox couple, it means that one molecule has to be from this, which is electron donor. Another molecule has to be from this, which is electron acceptor. So redox couples, they are arranged from the strongest donor at the top to the strongest acceptor at the bottom. So in case of having an ideal couple, we need to have strong donor and strong acceptor. So electrons can be caught up by acceptor at the intermediate level as long as the donor couple is more negative than the acceptor. So if the reduction potential of the donor is higher, more negative as compared to the reduction potential of the acceptor, then there could be donation of electrons from the more negative to less negative. So the greater the difference in the reduction potential between the electron donor and the electron acceptor, the more free energy is released. So let's say, for example, if we have this sulfate molecule, if this is reacting with, let's say, this water molecule, so there's a huge difference. But in fact, there's the highest difference as far as this particular tower is concerned. So there's huge difference in energy. So it means that when this particular reaction will be done, most amount of free energy will be released. So electron donors used in energy materials are also source of energy. So ultimately, this difference in the reduction potential is leading as a source of energy. So a very common carrier is the coenzyme nicotinamide adenine dinucleotide, or NAD+. So it is a electron plus proton carrier. It usually transports 2 electrons and 2 protons at the same time. So the reduction potential of NAD plus NADH couple is minus 0.32 volt. So which is quite high in the table. So NADH is a good electron donor. NADP plus NADPH is a related redox coenzyme in which a phosphate group is attached. Okay, so let's see this particular example. So here we have this NAD plus and we have a electron donor. A substrate is there. So when this NAD plus and the electron donor binds to an enzyme which has specific NAD plus binding site and the active sites. So upon binding, will lead to the enzyme substrate complex, and ultimately it will lead to a product. So what will be the product? The product will be this NADH will be reduced to NADH. So it will accept electrons from this donor. So this electron donor or substrate will be oxidized and this NADH will be reduced. So now this is kind of in the recycling process, or it's a cyclic process. So this NADH, now it will bind to another enzyme. Let's say this is enzyme 2 and it will bind to another electron acceptor substrate. So this is what we have, the electron acceptor substrate. And now we have an enzyme difference, so which will have a different kind of active sites. As you can see, the NAD plus and this NADH, there is conformational change. So now it will bind to another enzyme which has a different kind of active sites, and this electron acceptor molecule will also bind to this particular. Now there will have the enzyme substrate complex, and ultimately the NADH will release the electrons which will be accepted by the substrate. So in a way, now this NADH will be oxidized and this electron acceptor will be reduced, and we'll get something named NAD positive. So in a way, this is a cyclic process and which is going on inside the living systems. So energy rich compound and the energy store. So in living organisms, chemical energy released in redox reaction is conserved by the phosphorylated compounds. So usually there is formation of phosphorylated compounds. So the free energy released upon hydrolysis of the phosphate in these energy compounds is significantly greater than the average covalent bond in the cell. And that is the reason that the energy is stored in the form of phosphorylated compound. And it is kind of, when this energy released, it is conserved. So let's have a look at this particular table. So if you look at here, we have this phosphoenol pyruvate, bis phosphoglycerate, acetyl phosphate, ATP, ADP, acetyl CoA. So these, all the phosphate compounds, they have quite high energy, Z0 prime. And this particular, and if you compare with this AMP or glucose 6-phosphate, this is quite low. So these, in simple terms, PEP is quite high energy releasing compound as compared to AMP or glucose 6-phosphate. So ATP, so the most important energy rich phosphate compound in cells is ATP. So that's one of the reasons that we call ATP as the energy currency of the cell. So this ATP consists of the ribonucleoside adenosine, to which 3 phosphate molecules are bonded in series. So this is what the structure is. This is the ribose sugar, this is adenine, and these are the 3 phosphate molecules. So we have 2 anhydride bonds and 1 ester bonds. So when these 2 anhydride bonds are broken, so ATP, let's say, converts to ADP, and this ADP converts to AMP. So each will lead to a release of 13 kilojoules per mole of energy. So this is quite high energy. So then there's another energy molecule which is coenzyme A. So this coenzyme A derivative contains thioester bonds. So upon hydrolysis, these yield sufficient free energy to drive the synthesis of energy-rich phosphate bond. So this acetyl CoA plus water, ADP and phosphate leads to the formation of ATP. So this kind of, coenzyme A, it drives the formation of ATP from ADP. So energy storage, ATP is a dynamic molecule in the cell. It is continuously being broken down to drive anabolic reactions and resynthesized at the expense of catabolic reactions. So by this I mean to say that ATP is kind of going on into make and break pattern. So when there is a lot of nutrients, a lot of energy is available, it will be synthesized, and when the bacteria needs to do work, it will be used up. So ADP will convert to ATP when available sources are sufficient enough. This ATP will convert to ADP when the energy is required for doing work. However, for long-term storage, ATP is not a solution. So for long-term storage, what microorganisms do is they produce insoluble polymers. So these insoluble polymers, they can be catabolized when the high energy requirement is there, or let's say in conditions of nutrient are not that poor, there is a deficiency of nutrients. So these polymers could be glycogen, poly-beta hydroxybutyrate, or polyhydroxyalkanates. Some cases elemental sulfur that could also be stored in the sulfur chemolithotropes. Okay, so this is what I wanted to talk to you in this particular topic. So thank you very much for your time.